Thank you very much for having me here. And I will talk about a couple of works that I did in collaboration with these people here. This is Tita Chanda, that is now at ICTP. And Kuba, as we call him, Jakub Zagorewski, that is in Poland, and Maciek Lewenstein, that is at ICFO. That's me. Okay, so there are two papers here. One is on the out of equilibrium things. There is a bit is slightly older, and then there is one about equilibrium, somehow more recent. So let me motivate, even though maybe in this audience there is no need, why I want to study out of equilibrium and why I'm interested in universality. These are the two topics that I would talk about. One. The reason is that we are interested in these exotic emerging phenomena in many-body systems, but we know that we can't just observe the phase that we like, right? Typically, these phases are subject to some equilibrium conditions, so that we have some kind of compensation between energy and entropy, and these give rise to phase diagrams, right? In which, for example, if you look at the superconductor, we know that below a certain critical temperature and critical field, then the material becomes superconducting, but at higher fields and temperature, it's in the normal phase, right? And these all result of these kind of equations, right? The equilibrium physics. And so one interesting question is, if we go away from equilibrium, can we actually see the phase that we want in different situations, right? And the classical example of this is actually the Kapitsa pendulum, in which you would take a normal pendulum that has an equilibrium position when the pendulum is low, and it has an out of equilibrium kind of metastable state when it's high, and then by shaking its oscillation point, you can change this non-equilibrium state into an equilibrium one, right? And so you can see what wouldn't be an equilibrium state is becoming an equilibrium. And then from the point of material science and many-body physics, recently there have been a lot of experiments in which something of that kind happens, so in which you strongly drive your system out of equilibrium, and for some relatively long time scale compared to your driving, you see a phase that you don't expect to see at that temperature, at that value of your external parameter, or at least it seems to see something like that. And so this is one of the motivation why we want to move out from equilibrium, because maybe we can see more generic things. And then, so the point is that everything I'm discussing is in the context of many-body quantum systems. They are fairly complicated. And so there is actually a way to simplify the description if you happen to be close to what we call a critical point, in which many different systems behave similarly, and we have some kind of global knobs, or if you want, global degrees of freedom, for example, order parameters and things like that, that you can tune to and understand physics in terms of very simple power laws. And they tend to be pretty robust in the sense that, as I mentioned, there is not one single system that behaves like that, but there is a full class of systems. And they are all described by the same exponents, the same power law. And so this is a huge simplification. And so somehow, from my point of view, if you want, these critical points are the simplest many-body system, because we somehow know how the things should behave. Okay, and so, well, what's the problem then? Why don't we understand everything? Well, the problem is actually, as we know, the exponential complexity of many-body systems. So we actually struggle to write even wave functions. So if we have some Hamiltonian, so the sum of individual Hamiltonian, then we know how to diagonalize it and to find the eigenvalue and eigenvector. But as soon as we couple them together, then even, let's say, the wave function is exponentially complex. And so that's somehow the obstacle of all these many-body things. And I'd like to to think of our field of tensor network like a field in which we try to find these collective variables that allow to describe these states, right? And so think of a finite dimensional Hilbert space. This you all know. Basically, we have this coefficient of, so this tensor of coefficient that has exponentially many parameters. And now we re-express it. So this is exponential growth. And now we re-express it in as a function of a polynomial number of parameters, if you want. And this parameter probably have to do with something less local and more global than the original coefficient. And then that's the working horse for the results I will present today, right? This matrix product state decomposition that you're all well aware of. Okay, and so now I switch to the system I'm going to study. That is a bosonic gauge theory in 1+1 dimension. Bosonic because the matter will be bosons rather than fermions. Typically, in gauge theory, the matter are fermions and the gauge boson are bosons. Here, we are studying matter as a boson. And the original motivation for that was that in collaborative experiment, where these kind of system are being scrutinized in the lab, bosons are easier to cool down than fermions, basically. And so there is somehow an experimental motivation. And so if we study a one-dimensional system, the field theory that describes it in the continuum it has two dimensions. One, so we are working in two-dimensional field theories or path integral, if you want. And this is the action that you would write after a Euclidean rotation. So you have the standard. So now we just look at the gauge boson part. So you have the standard electromagnetic field strength. Since we only have two dimensions, it only has a 0-1 component. And then you can couple it to external currents. And the equation of movement immediately tell you that there are no propagating degrees of freedom and there are only constant, right? So electromagnetism in 2 dimensions is very different from electromagnetism in 3, okay? So this is 1+1 rather than 2+1, for example. So now if you add matter, the equation of motion get modified in this way. And so you see that basically you just have that your matter is necessarily confined because the energy, so here I add matter at L half, plus L half, and minus L half. And so we just get a constant field, we said, in between the two charges. And then as a consequence, the energy of that configuration is just the charge times the distance, basically, between the two. And so this energy clearly increases with separation. And so as a result, charges are confined. Okay, other question up to here? So we have no, I just repeat, we have no propagating gauge field. And as soon as we put matter into the game, this is all classical for the moment, but as soon as we put matter into the game, charges are confined because the electric field can only propagate in one direction and it creates a tube, right? Okay, so one question would be now, if you take these two charges and start to separate them apart, and now if we are in a relativistic system in which pairs can pop up from the vacuum, do you actually keep separating them until infinity? And the answer is no, because when the energy of your configuration is enough to allow the creation of a pair-antipair coupled from vacuum, and this will actually depend on the mass of this particle, then it is more it's energetically convenient to just pop up this particle from the vacuum, and then the kind of separate this kind of charge-anti-charge pair into two neutral excitation that moves, drift away. Okay, so in principle, we know that This is actually a process that is observed in nature, so it's called string breaking. So in principle, we would expect that if you construct this excitation in which we have a particle and an antiparticle on top of the vacuum, and then we let this particle propagate, we should see this phenomenon here of the string breaking. Okay, so this was, and this is the energetic, right? When the length is larger than 4 times the mass square divided by square. So we set up to observe this phenomenon with this MPS technique, and actually we saw that this doesn't happen, but let me go step by step. There was also an interesting paper here by the Trieste group, by Marton Cormos, Mario Collura, and Pasquale Calabrese and Gebor Tag. And what they did here, they were just simulating a spin model. So this is a Ising model with both parallel and transverse field. And then whenever you switch on a parallel field in the Ising model, then your domain wall gets confined in a very similar way in which I just described for these charges in an electromagnetic field. And so they have a very nice paper in which they study the effects of confinement into these light cone dynamics. So they start with a small kind of interface here, and then these couple of domain walls separate, but then at some point they merge again, and they slosh on forever and ever. And so this is a similar mechanism, but to the one that I will describe. But again, this is on a spin system, so on the Ising model, and I will describe it. I will describe a similar thing in the context of this Abelian Higgs model. Actually, what was observed here has a lot of relation with something that Luca also studied. That are called quantum scars. And actually, it's probably a different mechanism or a similar mechanism. I don't think we made up our mind. Maybe lately Maxim has a paper on that, and he has something to say, in which you actually take a very particular state that even though in general initial state of your system wouldn't thermalize, there are some specific state that evade thermalization. And that's what they call quantum scar, and there are other mechanisms besides this quantum scar in the paper in which that could happen. And I think that what I'm describing now is in loosely this category of, let's say, weakly non-thermalizing state in which you start from some initial state, and actually your dynamics is a bit trapped. But let me go step by step. So first of all, I apologize, I didn't define what I mean by thermalization, but in general, the idea is that if you start with your system out of equilibrium and you let it evolve and your system is generic enough, if you observe your system locally, after some time, everything relaxes. And it typically relaxes to something that is almost indistinguishable from what it would be at thermal equilibrium. Okay, so that's the definition of thermalization. So here, what is the system? We are working on the lattice. And the fact that we are working on lattice is encoded by this finite value of this value here. This is the lattice spacing A, and Q is just the charge of our particle. We have two species of boson because we want to describe a discretized complex boson. So we have one species that you can interpret as the particle, and another species of boson that can be interpreted as the antiparticle. And their hopping is mediated by this electromagnetic operator that, let's say, would flip the value of the electric field on a link whenever you make a particle hop. And it depends how it flips it, depends if it's a particle that hops or an antiparticle. Either it raises it or it lowers it in such a way that there is some kind of conservation. And so the Hamiltonian is really this electric field part for these links. So this would be the conjugate operator to this U. So it measures the electric field strength, is the square of it. And then we have a standard hopping term for the bosons. standard chemical potential for the boson. And then we have the hopping. You see that you have all possible combinations. Since we are relativistically invariant, we cannot say who is the particle, who is the antiparticle. So you have the all possible combination of hopping and pairing mediated by this U. Okay. So you see that you also and these factors here comes from taking the continuum theory, discretizing it on the lattice, so changing derivative by finite differences, grouping stuff together, and re-expressing everything in terms of this variable here. Any questions? So it's boson hopping. For the moment, they don't interact, but through these electric field variables. Okay. Okay, so the initial state, as I mentioned, is a state in which we create this particle and separate them at distance n divided by 2, when r from n divided by 2. So n divided by 2 is the center of our finite size lattice, and then we separate two particles. So we create a pair at distance r from the center, and we necessarily need to put this Wilson string that flips all the electric field along, because if not, it would just violate gauge invariance. Okay, and so this is our initial state. We start from the vacuum of the field theory or of our Hamiltonian that I just showed, so the ground state, and then quench it through this operator. And it's important to notice that this R in principle tells you how big is your quench, right? Because the farther away, the farther you separate the things, the higher the energy you inject into your initial state. And actually, we are always working in a situation in which we would scale N and R together. So we are always injecting some energy that, if you want, is proportional to the size of the system in a way. So that we are kind of doing a global quench rather than a local quench. So this may be important for what I will say in the following. So here is a cartoon of what we see happening. So here you have space, and here you have time. We create this pair here. And then you see we have depicted, for example, the positive charge and the negative charge in different colors. And then we see that initially they actually start moving as we expect ballistically. But then, exactly as Pasquale and collaborators saw, these cones get bent and they come back and they move again. And at some point, if the string would break, we would have expected that there would be a radiation of light mesons, right? And somehow an equilibration into a thermal gas of light mesons. So this would be the expectation if string breakings occur, right? Here, what I've depicted is some kind of string inversion, in which rather than the string breaking, it somehow becomes negative and attracted again, and that's how the things. So you create some opposite, some screening cloud if you want, and you get some string in between, and that's keep going. And so the question is, how does this process depends on the mass of the bosons, right? Because we saw that the characteristic length at which a string would break is a function of the mass of the boson. So the question is, how does this change as we consider heavier or lighter bosons? Okay, and these are the plots. So here the axes are inverted. So this is space and this is time in all the plots. And here I'm plotting the expectation value of the electric field on the links. And here I'm plotting these charge, the charge operator. I don't know if I define it, but anyway, it's just NA minus NB. I don't have it defined. But it's the density of A boson minus the density of B boson, okay? So this would be the charge operator. And then you see we have two lines. The first line is when the bare mass in my Hamiltonian is 0. So for light bosons, that's the lightest I can do if I don't put interaction, okay? And this is for a value of the mass that is large compared to the other energy scale. And so you see here, you see a kind of fish or double fish if you want, but you see a tail in which things seem to start to get equilibrated in a way. And so a natural question is, if I have very light bosons, so apparently we see the radiation of these mesons outside this cone, even though we see a couple of oscillation here, then it seems that at later times, this becomes thermal, okay? Or there is a hint that here things have equilibrated somehow. But as I will show you, you can't really see from this figure if that's the case or not. And so the two operator tells you more or less the same story, okay? Whether if you clearly increase the mass, you kind of get into a situation in which nothing happens outside of this blob that is oscillating, okay? So this is obviously non-thermal, okay? This state here is obviously non-thermal, and the question is, is this thermal? Question up to here? At a long time. So does it equilibrate for? Yes. So there is no meson operator, there is just the electric field for the moment. So the electric field, if you have a meson, maybe I go back here, you see that you would have an electric field connecting the two, okay? And then the other one is just the difference in occupation on every site between A and B boson, right? So it's here with a minus sign. So it's an on-site occupation NA minus NB. And this we define it as a Q on site. Okay, so these are the two operators that I'm showing here. Okay, other questions? Yes? Okay, the continuum limit would be taking x to infinity, right? So we are absolutely not in the continuum limit because if I remember correctly, x here is 2 or 3, something like that. So we are definitely on the lattice for these plots. And the reason why we stayed with this parameter were basically because we consulted our experimental colleagues, and these value that they could reasonably obtain in the lab were in this order of magnitude, let's say from 1 to 10, but they couldn't go much farther apparently. Okay. Any other questions? Yes. So these are, okay, so you mean between these two cases? So these are kind of prototypical example, right? There is a continuum from here to here, obviously, and you can go even to places in which nothing really moves because the bosons are actually infinitely massive, and then it would require infinitely much energy to kind of move them. But these are just two cases, but I think they are the most. So this is the most unclear, and this is the one that is more clear from my point of view. Does it answer what you were asking? Okay, so I continue. And so the message here is that looking at local observable, it's very hard to say anything. Yes, it seems to give you some. So you seem to have some difference, but what is the nature of these states at large time is very hard to address, right? So what we did was to study entanglement, and then it's just a simple entanglement of a bipartition of a chain with respect to the other. So we have 1D system, we cut it into pieces and look at the entanglement. And so here, I think the interesting plot is this one. So if you look at this plot here, this is all for fairly large masses, 1, 1.2, and 2. And you see that basically what happens is that you have an increase of your entropy on a certain scale, but then it either saturates if the mass is very, very large, so it doesn't, and it saturates to something that has nothing to do with the volume of the system, so it saturates much earlier, or it grows logarithmically. So you see this is time in logarithmic scale. So we push the simulation for a pretty long time. And you see this kind of very marked residual oscillation. So this system is clearly non-thermal. This oscillation, again, has to do with this bouncing of the particle up, out, and in from your cone, okay? So, yes? Well, it's not local because so you have to define what local means. Well, the point is that you're creating, so you're injecting an extensive energy on the top of the ground state, right? Because you're stretching this string to very long distances, right? So actually, that's one of the things. What is the overlap of this state with the higher energetic state of your system, right? And as you mentioned, there is something. So what we are doing is actually state that in order to, so we have very small, if you want, operators, elements that actually couple this state to the very excited state. But it is still a state in the high part of the excited spectrum, right? It's not a local excitation in the sense that we have a lot of energy into the string. So it's true that at the boundary, if you want, it's almost like a local excitation, but we have somehow flipped the electric field along all the half of the system, if you want. So yeah, exactly. Is not sorry. No, indeed. No, it's a very specific initial state. I agree. So that's one of the points, right? It's a very specific initial state that is highly excited because the protocol that I used was that every time I would increase the system size, I would also increase the separation. So R divided by N is constant, equal to, I don't know if 1/2 or 1/4, so something of the order. So it grows with the system size. So the larger system size, the higher the energy, but it's definitely a very specific state. And I agree. So it's not like just rotating slightly the electric field everywhere, or rotating. Yes. Yeah, logarithmically, yes. No, indeed. So it could be, so on exponentially large time scale, it could be that these things actually thermalizes. So yeah, I don't know if scars also are like that or not, but it's definitely something that for very long time evades thermalization and maybe eventually will thermalize on an exponentially long scale, exactly because of the same reason. So you have exponentially small matrix element between this excited state and typical state in that energy window that are kind of eigenstates. Or maybe it's even worse. So it's locally very similar to an eigenstate, probably, because it's just flipping all the electric field. Is still a very excited state, but it's an eigenstate, right, of the electric part of the Hamiltonian list. So when this so there are several. I don't know. I'm not an expert. I think Vlaco can maybe help there. But there are several features of the state that make it kind of stuck. No. Mm-hmm. Mm-hmm. Yeah. But it's exactly. It's definitely in that case. It's definitely non-thermalized. But I think it's even more interesting this case here, where the mass is 0, even though from what I will say later is not very different, because what we'll see later is that we are still deep in the confined phase here. So even though the bare mass is 0, there is actually, there is actually a mass for these things coming from the fact that it interacts with the photon. But you see that even here, so if the system were thermal at a very large time, then this curve should be something that I should normalize with respect to the volume of the system, right? In order to get different system size curve together. So these are different system size curve, this different color. And you see I have to multiply by some power of logs here. And that's clearly not the thermal value. Okay, so this entropy of the final state is clearly non-thermal. Okay, and we don't see any volume law. Yes, they are just fitting parameters to get this collapse. Okay, so we don't really understand well where does this formula comes from. It's just from trial and error, but it looks like this kind of normalization brings the curve almost one on top to the other. Okay, okay, and then it's much easier to see this if you use this symmetry resolved entanglement, as Herman would call it, or distillable and classical entanglement that Yuto and Frank would call it, and concentrate on the classical part of it and on the configurational entanglement. So there are several names given by the fact that your density matrix is block diagonal. And so you have some entanglement inside the block and some entanglement between the blocks, right? And so this is the part of the entanglement between the blocks. And you clearly see that is clearly non-thermal in the sense that you still have a very big tail in the middle of the system, even though from the local operator you wouldn't have said that, right? So you have to compare this with the initial fish that we had, right? In which we had this queue of the fish spreading more or less uniformly. Here it's pretty clear that there is still a signature of the initial state in your final evolution, okay? And so I think it's a finer way or an easier way to distinguish this, okay? So I hope I have convinced you that there are these initial states in this gauge theory that evade thermalization for a very long time. And the reason for that can be maybe related to these almost, let's say, fracton physics. But I mean, there are several ways of attaching it. There are several reasons. But clearly, the mechanism is that the energy is conserved in order to get to other state. You have only the hopping. It hops to different energy states. So this is suppressed. And somehow all the available states are somehow off resonant. And the ones that are resonant are exponentially suppressed because you have to hop kind of at the same time the left and the right thing in such a way that the strings keep the same length. And so these are very exponentially suppressed. So this is a kind of hand-waving argument, but that's the best we have for the moment. Okay, so if that's fine, I would pass to the second. I don't know if you have any question on this part. If not, I would pass to the second part. Yes. That CERN can work. Well, I guess so. Why do you say that CERN? Yes. Yeah, it would be. Yeah, yes. Yes. Yeah, yes. I think yes. I think that's part of the thing. I think that here dimensionality plays a big role. Probably if you repeat this in higher dimension, you have more path to kind of go around, and maybe the string would just break much easier. Even though I saw some Monte Carlo studies, so some lattice QCD study of the string breaking even in 3+1, and apparently it doesn't break where people expected it to break. So there is something there that is unclear, I would say. But again, I'm not an expert. Yes. Yeah, sure. It becomes just a kind of almost free particle, right? Once you have a meson of a given size that is given by the string strength. Yes, not the string strength, but the string tension, sorry. Yes, yes. Yeah. There is actually. So that was the point. So even though I grow the system, so as I grow the system, I inject more and more energy to the initial state, and the mass of the boson is fixed. And even though the mass gets renormalized, so it's not zero, but it is renormalized because it interacts with the photons, it's a finite value. And in principle, I can take these things to infinity, but nothing would change. So it's not a matter only of energetics, but it's a matter of operator elements that connect that state with the state with the broken string, and they are exponentially suppressed. Okay. Okay, can I switch to the equilibrium part of it? So exactly. So once we saw that, I started to think, okay, let's see what happened with negative mass, and we switch on the interaction, and we try to really go to a place where these bosons are light, right? But then I went back to my books. I invite you to read the chapter on the Abelian Higgs model in that book, and I realized that actually there is not such phase in which bosons are light in the continuum, because basically this is the same thing where I now also put interaction, right? The boson interact via Fi to the fourth term, and some background field, this theta term that is here. Okay, so we said we have a constant. The electric field can be constant, so I added this theta term. Physics is periodic in theta. I don't have time to explain it, but it's easy to understand that physics is periodic in this variable, in this constant here. And so this is the phase diagram that you see in the books. And basically, what I was discussing was at theta equal to 0. So on the other face of this cylinder. And if you go to the books, you discover that there is nothing going on there. So on the other side in the continuum, on the other side of the cylinder, there is just a single phase. And you can somehow understand it by appealing to non-perturbative. So this is a typical pedagogical introduction to instantons. So if you go and look into the book, they explain you how you would have an Higgs mechanism with a symmetry breaking, so an Higgs phase and a confined phase, but due to instantonic calculation, this gets screened and you always get the same stuff, okay? So there is only a single phase. And so what we see on the lattice is actually different in the sense that we see at theta equals 0, similar things to what you would see at theta equal pi in the continuum. And as discussed with Antoine, probably there's nothing to do with the continuum physics, but still, I think it's interesting to see it, right? So this is our sketch of the phase diagram, and now we'll discuss a bit more on it. But the take-home message is that we find in the mu lambda plane, so mu is the mass, and lambda is the interaction. So we find a confined region and a Higgs region, so they are connected. So they are not phased. They are kind of qualitatively or quantitatively different regions, so where something is larger in one side than the other. And then among them we find, or between them, we find this first order line that terminates in a critical point, okay? And so most of our effort was to locate this critical point and understand what is its nature, okay? And actually this is still ongoing, so we only have a partial explanation. So here is the results of a lot of computing hour and numerics done by thetas. And so again, here I'm plotting O-tunneling would be just the expectation value of this operator here. So phi dagger is defined, so phi is defined here, is a superposition of destroying an A boson and creating a B boson, okay? And pi is the conjugate moment. And so this is the, again, invariant operator again. So we can plot this operator here in this phase diagram, and you clearly see that there are some distinct features. So here it's very small, it's almost white, let's say, and then on this side it becomes larger. Okay, so there are two different regions. Yes, I'm almost done. There are two different regions. And the same can be seen by looking again at the entanglement entropy of a bipartition. You see that there is a region in which the entanglement entropy is pretty small, and then there is a region in which it grows, okay? So here, as I mentioned, we have a first order line, and then there is this second order critical point at the end of the line. And so first I want you to convince that there is a first order line, and you can see these plots here are, for example, O tunneling as so some kind of section here, horizontal section. O tunneling is a function of mu over q, and you clearly see jumps, right? If you look at the energy of the ground state, you see a kink. If you look here at the derivative, you also see this jump. And the entropy saturates, as you would expect, at large size. It saturates, it doesn't keep growing. With system size, it becomes constant. So we have a massive phase with a jump, okay? Any question about that? Do you agree that it's a first order transition? Yes, very good. And then we scan the things, and we arrive to this critical point here. And the question is, how do you locate it? Well, now what we do is we assume there is conformal invariance, and then one could kind of discuss about that. But if we assume there is conformal invariance, we have this formula that comes from CFT about how the entropy should scale. And it should scale with the prefactor that is known as the central charge, and then it's a function of W. And W is just what is called the logarithm of the length coordinate. So it's some logarithm of the sine of pi L divided by L, where L is the partition size and big L is the system size. Okay? And so if you express all your entropies for different system size and different partition as a function of W, they should scale at the critical point like that. And then you could actually look, you see these are different system size and different and different curve. You could actually look if you find something like that in your data, and you happen to find a crossing point, okay, for this coefficient. So this is the coefficient extracted by fitting this formula here, right? You write all your entropy as a function of W, you fit it with a linear thing, you get a coefficient here divided or multiplied by 6, and that's what we get, right? And so we see that they cross at a certain value of the things, and interestingly, what we call it the central charge from the fit is 1.5, okay? 3.5, as Natalia also had. And you can also look at the scaling of the full different bipartition at that specific point. That is, this point here is somewhere here, as a function of W, and you see that they all collapse pretty perfectly on the same line, right? So the fit is good, okay? And you see the slope is 1.49 divided by 6. Okay, so that's an indication that the central charge, if there is a CFT, so there is a big if there is a CFT behind this critical point, this central charge is 1.5, okay? And how could you understand this from a naive picture? Well, we know that in 1 + 1D there is no Higgs mechanism, right? Because of these instantonic effects. But if you go back to the whole description of the Higgs mechanism, then you would have that your complex scalar has a kind of a phase and the radial mode, right? To real field. And then the phase undergoes an Ising transition, is a lambda phi to the fourth, so it's an Ising universality class because it's a real thing. So it goes from not being not having a vacuum expectation value to having one, so to polarize from order to disorder or vice versa, and the phase gets eaten by the photons, and typically you get the Higgs mechanism, so you get a kind of you give a mass to the photons, but in this case we actually get a dynamical boson, right? So we somehow reintroduce the degrees of freedom that you would get if you would be in higher dimension. And so my naive picture is that this piece here, together with the photon field that isn't there typically, becomes a free boson, okay? So this is only a naive picture that we are trying to make sense of. And that's a bit the story. So if you look at certain correlator here, you see kind of Luttinger liquid-like physics because you see one exponent and it is inverse. So you look at this pi dagger pi correlator, it decays with a power law as a function of delta, and this one also. This increases, so we have a boson, so the boson is not himself a primary field, so it just goes logarithmically with things, and so it goes with the exponential of omega. Omega is the log, so exponential of omega, and so here you increase logarithmically, so omega is the log, so this increases logarithmically, and this is exponential of the log is just the things, and it goes as a power law, okay? So the derivative, if you want, of the bosonic field is a primary field that there is a power law decay. Okay, and then one of the questions is, are we really seeing a conformal field theory or not? And one way to see it is actually to look at this Casimir effect and see if it's linear in the system size. And actually it is to a great precision. So you see we have this term here that somehow encode your dynamical critical exponent kappa, and in this case it seems to be 1. Okay, so somehow this assumption that we have that we are dealing with a Lorentz invariant or a conformal invariant system apparently is correct. And we get this number here also. And so summing up on the lattice, so not in the continuum, it seems that we found another first order line of transition with a C equal 1.5 critical point here. And actually the question is now, if we move theta, actually what happens, right? We know that here we have an Ising critical point from in the continuum. With a first order line, and it's terminating in the Ising critical point. Here we have a C equal 1/2 thing, so probably there must be a flow from this one to this one, and somehow the boson must become gapped out during the flow, right? But it's something we haven't explored, and we need to kind of explore further. Yes, thank you.